Let us consider a simple reaction. Substance A converts into substance B. This is a reversible reaction. The blue particles represent A, and the red particles represent B. At the beginning, the container is filled only with A, the blue particles. Over time, some of A converts into B. As more and more B forms, some of those red particles begin to convert back into blue particles. If we look at a concentration versus time graph, at first the concentration of B is 0, and the concentration of A is high. As the reaction proceeds, the amount of A decreases while the amount of B increases. Eventually, both concentrations level off. They do not have to be equal to each other, but they both become constant. This state is called chemical equilibrium. Now let us look at the reaction quotient, which we call Q, and the equilibrium constant, which we call K. When Q is less than K, there are fewer products than at equilibrium, so the reaction shifts to the right, producing more products. When Q is greater than K, there are more products than at equilibrium, so the reaction shifts to the left, producing more reactants. When Q is equal to K, the system is at equilibrium. This leads us to Le Chatelier's principle. When a system at equilibrium is disturbed by changes in concentration, pressure, or temperature, the system shifts in a direction that minimizes the effect of the disturbance. This restores equilibrium. For example, imagine a balance scale. If you add too many products, the system shifts toward the reactants. If you add too many reactants, the system shifts toward the products. Now let us look at solving equilibrium problems with an ICE table. ICE stands for initial, change, and equilibrium. Use an ICE table when you know two of the following pieces of information: initial conditions, equilibrium conditions, and the equilibrium constant. It is most common for such problems to ask for the equilibrium conditions, but you will always be given two pieces of information out of these three. You should be able to use an ICE table to solve for whichever piece is missing. The first type of ICE problem is when the algebra leads to a perfect square. In that case, you can take the square root directly. We can plug the initial concentrations into the I row. Since the reactants are being depleted, and hydrogen gas has a coefficient of 1 in the balanced equation, we write minus X. The same applies to iodine gas. For hydrogen iodide, since it is a product, more of it will be formed. Because it has a coefficient of 2, we write plus 2x. Next, we substitute these expressions into the Kc equation and solve by taking the square root and then solving linearly. The value of x is then substituted back into the E row to find the equilibrium concentrations. We will apply the same method to this problem. Here, since Kc is small, there will be very little shift to the right, meaning the reactants are favored. Thus, in the denominator, 1.2 minus x is approximately equal to 1.2, which makes the algebra much simpler. Finally, we can verify that our approximation is valid by checking that x divided by 1.2 is less than 5%.